So I will talk about Skolem sets. It's a very different Skolem business than the Skolem you heard about yesterday, but it's the same Skolem, the same Thorolf Skolem, who was a logician, a model theorist, a number theorist, an algebraist. He did lots of mathematics. I should say a few words about this area. So the broader area is dynamical systems. I've been working in this area sort of seriously, I would say, for about 15 years. And coming before from time in Automata, where I collaborated with people at the IFCPAR quite substantially. And the very first talk I gave on this area, this dynamical systems area, this column, I actually gave at IFCPAR, so spiritually here. And Paul was in the audience. Where's Paul? Do you remember, Paul? The very first talk in 2008, I was professeur invité in Cachan, and that was the very first talk I gave, which was a board talk. And I didn't know that it was really going to, continue, and that 15 years later I'd still be working on these things. But here I am. So here we are, and the problem is still not solved, as you will see. Now. Perhaps something else I should mention, this is joint work with several people. Their names are there. So James Worrell is, I think several of you know him. He's a longtime collaborator of mine. Florian Luca, James Maynard, and Armand Nubisi are number theorists. And in fact, I learned that Paul had initially considered me a number theorist. So if you'd done this, Paul, perhaps we would have collaborated on this stuff, and then your name would be there instead of one of these people. So who knows? So Armand is a postdoc in my group. Florian is he's a Romanian number theorist who lives in South Africa, but last 3 years has been spending most of his time in Saarbrücken in my institute. And James Maynard is a colleague from Oxford. So without further ado, let me just ask actually, this Skolem problem that I'm going to talk about, some of you know about it. Does anyone somebody never heard of this problem? I'd just like to get a sense of yes, Pascal. So don't be shy. Okay, so about a third of the room, but just to check, who has actually heard of the problem? Okay, so that tallies up. Okay, I will introduce it, don't worry. Let's go. Oh, hang on just a sec. I need to agree to the recording. And no, I need to do this, I think. There we go. Okay, so I'll start with just a little quiz, a little problem. You have a program here, very simple program with 3 integer variables, initialized 1, 0, 0, and you say while x is not 0, do the following linear or affine assignments, right? And the question is, does this program halt? Okay, and you can sort of think about it, and it's kind of not obvious either way, right? You can try, and how do you determine whether these kinds of simple programs, it's a simple while loop with linear assignments. The general form is that you have x, which is a vector of variables, x1, x2, x3, etc. You initially assign it to a bunch of integers, and now you say, as long as the first variable x1 is not 0, do this linear assignment. Okay, this is the more general form. And the question we're asking is the decidability of whether, given such a program, whether it halts. Okay, is this problem decidable? Or, and that problem is the Skolem problem. And this is Thorolf Skolem. So that's equivalent, at least, to the Skolem problem. Okay, does that make sense? So it's a halting problem for a very simple class of loops. Now, the more classical formulation in his 1934 paper, when Skolem discussed some of these things, he didn't phrase it in terms of programs. Of course, programs and loops and so on didn't really exist, but he phrased it equivalently in terms of linear recurrent sequences. So what is a linear recurrent sequence? It's a sequence of integers that satisfies a recurrence relation, a linear recurrence relation. So the n plus kth term of the sequence is these are integers, right? Is a1 times the n plus kth minus 1 plus a2 times n plus k minus 2, etc., up to ak times un. And the most well-known example that I think absolutely everybody knows is the Fibonacci numbers that obey the recurrence, the well-known recurrence. Un plus 2 is un plus 1 plus un. So here a1 is 1 and a2 is 1 as well. And the Skolem problem phrased in this context is you're given the instance, you're given a linear recurrent sequence, so given by the initial terms and the coefficients A1 to AK, and you ask, does it have a 0? Okay, and that's actually equivalent. It's not very hard to prove the equivalence between those two problems. Okay, that is the Skolem problem. And remarkably, this problem, the decidability of this problem is still open. Okay, it's quite stunning. Terence Tao wrote about this some years ago. He said it's famously outrageous that this problem is still open. It's saying that we do not know how to decide the halting problem even for linear automata. The linear automata he refers to are these little, simple while loops. And De Clipton on his blog said, look, this is a mathematical embarrassment. And in a paper a few years later, he wrote, arguably by some distance, this is the most prominent problem whose decidability status is currently unknown. Okay, so this is an important problem. Decidability is open, and I'm going to tell you a little bit about it in this talk. But before we do this, I'll have a quick quiz. Which of the following problems are decidable? And for bonus points, for those that are decidable, what is the complexity? And I know we have some world experts in automata theory, so I expect some people will actually nail down the precise complexity of whichever of these problems are decidable. So let's read these problems together. So you're given two automata, and I follow Volker's lead here. These are NFAs. NFAs are finite words. Two automata A and B, so NFAs are finite words. And you're asking the following question. Is there some word length n such that A and B accept exactly the same words of length n? So for instance, maybe the word length is 7, and A and B accept exactly the same words of length 7. Okay? But maybe that length is 13 or something. But that's a question. Okay. A second problem looks quite similar. You're given again two automata A and B, two NFAs A and B. Is there some word length n such that A and B accept not exactly the same words, but the same number of words of length n? So maybe of length 7, A accepts 3 words and B accepts also 3 words, and that would fit the bill. They're not the same words, but they're the same number of words. And the third problem, it's about Markov chains. If you don't know Markov chain, just ignore this problem. It's just an example, but you have a discrete Markov chain over states S1 to Sk. Rational transition probabilities. You start in state S1 with all the mass in S1, probability 1, and you ask, is there an integer n such that after n steps, moving in this Markov chain, the probability of being in state Sk is exactly 1/2. Okay, so I'll let you look at these problems just a little bit. And I want to know which of these problems are decidable, which are undecidable, what's the complexity, anything you can tell me about these problems. So I'll let you think about it, just 30 seconds or so. Sorry? A Linus sequence? I don't. I don't. No, I don't know that. I don't know how to do this. So tell me what you think then. Yes, no, no. Yes, no, yes. I see.
So the third one has a flavor of the Skolem kind of a thing.
Okay, which one?
The last one.
The last one. Okay, so here we're told this has a flavor of the Skolem problem. Okay. Any other guesses about any of these three problems? Anyone? The second one is a Skolem problem. Very good. Second one is a Skolem problem. And the first one? Decidable. Very good. It is decidable. What's the complexity? Exponential time. Very good. So the first one is decidable, and it's nx time complete. This is non-trivial. The decidability is trivial. Nx time completeness is not trivial. The second one is Skolem complete, and the third one is also Skolem complete. Okay, so the point of this little quiz is to show you that these Skolem problems sort of arise perhaps in places you would not necessarily expect them to, right? Yeah. Interreducible with a Skolem problem in polynomial time. Yeah. Yes, it's even more than a Turing reduction. It's a Cook reduction. It's a 1-to-1 reduction. Yeah. Okay. So some other application areas. So these are areas in which, I swear to God, there's at least one paper that is related to Skolem problem. We've heard of L systems. I'll come back to this in a second. Software verification, dynamical systems, differential privacy. There was a paper at ICALP, I think, a few years ago. Weighted automata in games, obviously, stochastic systems, and so on. So this sort of appears in a lot of places. Here are these L systems. I did not coordinate with Volker, but I like these. I like these systems. And indeed, there were some books in the 70s which sort of led to the closing of the field. And there has been a revival because Jutta Hein in Oxford last year taught a course in computational biology in which he introduced L systems. So I think somehow these guys are coming back. And this Skolem problem is mentioned here, also the positivity problem and so on. So these problems, these arise in terms of understanding the rate of growth of these trees. These L systems are models, computational models of plant growth, of biological growth. And if you want to know the rate of growth of these trees, the Skolem and the positivity problems play a key role there. We also heard about a couple days ago about power series automata and power series, and we have some world experts in the room on these topics. And in both of these books, this is, I don't know if you can see, this is the Rottenauer. This book was mentioned, I think, in a couple of days ago. These again are closely related. These questions are closely related to the Skolem problem. I could say more about this, but I won't right now. But happy to talk about it afterwards if anybody's interested. So I will now tell you about the Skolem-Malolek theorem. I'm just curious, who has heard of the Skolem-Malolek theorem? Aha, okay, we're thinning the, okay, so Jacques, of course, and okay, so we have couple people who do. So let me tell you. Before I tell you, I just want to state a fact, which I'm not going to prove. It's not such a deep fact or anything. Any linear recurrent sequence can be effectively composed into finitely many non-degenerate linear recurrent sequences. I won't tell you what that means. It's a criterion. And it can be done. So you can work with non-degenerate, you can assume non-degeneracy. Okay. So we just take it for granted, and we go with the flow. Now you can state the Skolem-Malolek theorem in this way. So this was proven by Skolem in this famous 1934 paper. Then there was a version the following year by Mahler, which extended the work a little bit, so from integer to sequences to complex algebraic sequences. And again in 56, Lech proved it over all fields of characteristics 0 in 53. And then Mahler did the same thing in 56, not realizing he had reviewed the 1953 paper. He'd forgotten about it, apparently. But anyway, the theorem is associated with these three people. And what does it say? So you have a linear recurrent sequence. Let's assume it's non-degenerate, whatever that means. It's a non-degenerate linear recurrent sequence. So Fibonacci is a non-degenerate linear recurrent sequence, for instance. And you want to know the set of zeros. So the set of indices n, such that un is 0. And that set is finite. Okay, this is what the Skolem-Malolek theorem tells you. It has finitely many zeros. So if you take a polynomial in one variable, again, this is a linear recurrent sequence, by the way. So p of 1, p of 2, p of 3, the sequence of numbers you get, if you have a single variable polynomial and you plug in p of 1, p of 2, p of 3, you get a linear recurrent sequence. Okay, so it generalizes polynomials. Of course, you have finitely many zeros. But this is also true for linear recurrent sequences, which are more general. And the decidability of the Skolem problem is equivalent to being able to compute this finite set of zeros. Okay, so it's interreducible. But unfortunately, all the known proofs of this theorem make use of non-constructive p-adic techniques. It's a beautiful proof, by the way, the Skolem proof. It's absolutely beautiful proof. And I was hearing earlier that computer science is closer to algebra analysis, but it's actually a p-adic analysis proof. And I like it very much. Okay, so let me say a little bit more about these LRS. So suppose that you have a linear recurrent sequence that satisfies a given recurrence relation. We define the characteristic polynomial of the sequence as such. So it's a polynomial in one variable. So chi of x is x to the k. minus a1 x to the k minus 1 minus a2 x to the k minus 2 dot 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 minus ak. So it's just a definition. And then the characteristic roots, the roots of these characteristic polynomial are the algebraic numbers that you get when you solve this. And then it turns out that you can always have a closed form for un in terms of these characteristic roots. So it's going to be a finite sum of polynomials, say univariate polynomials in n times lambda j to the n. Okay, where lambda 1 to lambda m are all the characteristic roots. Okay, and these polynomials have algebraic number coefficient, complex algebraic number coefficients. Okay, now this is well known because the Fibonacci sequence again is of that form. So the polynomials here are constant polynomials, 1 over root 5 and minus 1 over root 5, and the characteristic roots, you have the golden ratio and its Galois conjugate, and they're raised to the power n. So it's exactly of the form that we had here, okay? And we say that a linear recurrent sequence is simple if the characteristic roots are not repeated, if they as roots of the characteristic polynomial. So far, so good? Okay, so equivalently, an LRS is simple if all the QJ are constant. So in Fibonacci, again, like I said, these QJs are just 1 over root 5 there. So it's an if and only if. So the QJs are constant if and only if the sequence. And the vast majority of LRS are simple. So if you put any kind of reasonable probability distribution on LRS and you pluck one at random with probability tending to 1, it will be simple. And simple LRS correspond to diagonalizable matrices. If you think back to my very opening slides when I had this matrix, so when the matrix is diagonalizable, the attendant linear recurrent sequence is going to be simple, and conversely. Okay, all right. So what is known about the Skolem problem? Well, the only unconditional decidability results that we have are at low orders. So if the order is at most 4, I forgot to say the order. The order is the number of previous terms that a given the next term depends on. So Fibonacci is order 2. Because un plus 2 depends on the previous 2 terms, un plus 1 plus un. Okay, so if you depend on the first 3 terms, then you're order 3. We can do it up to order 4, equivalently for 4 by 4 matrices, but we do not know how to do it for order 5. So this is a deep result independently by Mignot, Shor, and Tiedemann. These are number theorists, and Vereshchagin, who proved in the mid-80s. And this is a difficult result. And the critical ingredient is Baker's theorem on linear forms in logarithms, which earned Baker the Fields Medal in 1970. So it's using some non-trivial tools. And just as a note, even for simple linear recurrent sequence, we do not know how to decide the Skolem problem at order 5. Okay, even under the assumption of simplicity. Okay, now what do you do when you're stuck? You bring in additional tools. In particular, you can bring in conjectures. There is a long tradition in mathematics and computer science of establishing conditional results. So this conjecture implies, this result. So for instance, Miller's polynomial time algorithm for primality testing relied on the generalized Riemann hypothesis. Okay, so the correctness of the algorithm relied on the generalized Riemann hypothesis. Now, of course, we know that primality testing is polynomial time, but that took another, was it 30 years or something? The security of RSA, and pretty much all of modern electronic commerce, is based on the conjecture that factoring is hard. If factoring is shown to be easy, then we really got to scramble to replace, when you send your credit card information, it's secured using RSA, and so everything would collapse until we put something else in place. The decidability of the first order theory of real arithmetic with exponentiation is a famous result by McIntyre and Wilkie, but it relies on Shanuel's conjecture. But here, interestingly, Shanuel's conjecture is only needed for the termination. The correctness of the procedure is unconditional, which is very nice. It's a much nicer situation to be in, because whenever you finish your procedure, you know that your result is correct. And in fact, you have a certificate. And finally, there are many, many results subject to p not equal to np or the exponential time hypothesis. You open the proceedings of a stock or Fox or soda, and you say, assume p is not equal to np, then blah, 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 and so on, right? So these are kind of often hypotheses that are being made. Okay. So now let's look now at I want to talk a little bit about the Skolem problem for specialized to simple linear recurrent sequences, conditional on some classical conjectures in number theory. And so this is a paper that we published last year with some other co-authors. there is an algorithm which takes as input a simple non-degenerate LRS and produces its set of zeros. Okay, and the termination of this algorithm is guaranteed if you assume two classical number theoretic conjectures. The first one is the p-adic-Chaniol conjecture, and the second one is the so-called exponential local global principle. I won't tell you what these things are because I want to talk about universal Skolem sets, but just to say that these are two classical number theoretic conjectures, and they're only needed to show termination, that our algorithm will terminate. The correctness of the algorithm is unconditional. And indeed, when the algorithm terminates, it produces correctness certificate. It says these are the zeros, and moreover, there's a proof that there's no other zeros. Okay. And in fact, when I presented this at Formats, Paul was there as well, I believe, right? This was last year. And we have a tool. We've implemented this. We rarely implement things, but we have a tool. Here's a screenshot. If there's some time afterwards or people are curious, then I can show how this works. And these are the sort of the certificates, as it were. So you can if you go on my webpage, you go in software. It's actually skolem.mpisws.org. You can actually play with this tool. It works well. It works fast, and you don't need to install anything. You just And there are examples that are pre-loaded. So if you want to just you have the input format. It's very simple. Very easy to play with. Okay, so I want to come to the main point of my talk, which are these universal Skolem sets. And so let me define. So this is a new line of attack on the Skolem problem that was initiated 2 years ago. The first paper was at LIX 2021. And so let me define what these things are. So an infinite set of numbers. So S is an infinite set of integers. We say that it's a universal Skolem set if there's an effective procedure that takes any non-degenerate linear recurrent sequence and tells you and gives you the set of zeros that the sequence has in this set. Okay, so I've got an infinite set S, and I can compute in this set what are the zeros of UN. Not all the zeros. If there are zeros outside of the set, I don't know. But I can give you all the zeros that are in this set. This set is fixed, and this has to work for any possible LRS. Okay. Right, this is definition. Doesn't mean these things exist. It could be a unicorn or something like this. But just so that we understand, we make sure we understand what we're talking about. So equivalently, S is a universal Skolem set. If given any non-degenerate LRS, you can decide whether the LRS is 0 in S. Okay, so because there are only finitely many, and you can always shift an LRS, so you get rid of the first zero, and then you ask again and again and again, and at some point it says there are no more zeros, it's equivalent. Okay? And the decidability of the Skolem problem is equivalent to proving that N is a universal Skolem set. But in fact, it would suffice to show the existence of some universal Skolem set that contains some infinite arithmetic progression. So for instance, if you have a universal Skolem set that contains all the odd numbers, you've won. You've solved the Skolem problem, okay? Or every multiple of 3, or any infinite arithmetic progression, even from some point on, you have won. Okay, but maybe these things don't exist. Now, why would you think they might or might not exist? Well, if you try to do the same for Turing machines, a universal halting set. So let's say, given a Turing machine, you consider its halting set, which is the set of integers, such as after n steps, it halts. Okay, so you want to you have the halting, let's say I would call it the halting spectrum of a Turing machine is a set of n, such that this Turing machine halts in n steps. Now, could I define an infinite universal halting set? So, given any Turing machine, I can decide if I can decide whether it has a number of steps n, such that it halts in n steps, and n is in my my universal halting set. Okay, this cannot be done. It's an easy consequence of Rice's theorem. You can also see it directly. It could not exist, right? A universal halting set for Turing machine can't exist. So it's a little bit surprised that, in fact, universal Skolem sets do exist. And the first that we constructed was in LIX 2021, and it's a very simple set. It looks a little bit complicated here. It's actually very simple. And let me explain to you how it works. So you have a function f from the positive integers to the integers, where f of t is the floor of the square root of log t. Okay, log is a natural logarithm. And you set s0 to be 1, and st is t factorial plus s sub f of t. And now you collect in s, s1, s2, s3, s4. And the claim is that this is a universal Skolem set. Okay, so I'll let you digest this a little bit. So first of all, the function f, it takes a large number and it produces a much smaller number. F is a decreasing function. So when you recurse and you do s sub f of t, you will clearly bottom out to s0 fairly quickly, right? Because you're taking square root of log t, so quite quickly you will come down. Okay, and so if you calculate the first members, you've got 1, then 1 factorial plus 1, 2 factorial plus 1, dot, dot, dot. Finally, when you reach 8 factorial, okay, then you get 8 factorial, and when you do square root of log 8, you actually get 2. So in the floor, you get 2, so you get plus 2 factorial, and then plus 1, dot, dot, dot. So if you actually write out these numbers, it's a sequence 1, 2, 3, 7, 25, and so on. So it's quite sparse. Okay, all right. So I've defined the set, and I claim it's a universal Skolem set. So it's a set consisting only of sums of factorials, by the way, right? And maybe it's a little bit surprising. So I want to explain to you why it's a universal Skolem set. Okay. So the Skolem universality of S. So here's just a definition so that we keep track of it. So first, a proposition. So given an LRS UN, and any prime p such that p does not divide delta, I'll tell you what delta is in a second, then for all t and L in n with t greater than p to the d, I'll tell you what d is in a second, u sub t factorial plus L is congruent to ul mod p. Okay, this is what I want to show. So here, delta is the discriminant of the splitting field of the characteristic polynomial, and d is its degree, the degree of that splitting field over q. Never mind what these things are. And people like Volcker, who studied algebraic number theory, they understand these things, but it doesn't really matter. Just go with me, and when I need properties, I will just tell you what they are. But I want to show that in general, u sub t factorial plus L is congruent to ul mod p for most primes p. Okay, so primes p that satisfy these things. So the proof sketch. So you write un in this exponential polynomial form, right? Now you recall Fermat's little theorem. So this is for integers. If a prime p does not divide a, then a to the p minus 1 is congruent to 1 mod p. Okay, so I think we recall this. Most people have remember this, recognize this. There's an equivalent version for algebraic numbers, algebraic integers, except you have to raise an algebraic integer. These lambdas are algebraic integers, by the way. I mean, there's not just algebraic numbers, they're actually algebraic integers. You have to raise this to the p to the h. H is the inertial degree of the prime. Okay, never mind. But the point is, if you raise it to that power, then it will be then this lambda to the p to the h minus 1 is indeed congruent to 1 mod p. So when you have this, so you take lambda j to the t factorial, and t factorial, t is bigger than p to the d, and h is going to be smaller than d. So here you will have a factor in this t factorial. You get all the product of all the numbers up to t. You will certainly have a factor of ph to the minus 1. That's going to be congruent to 1. So whatever remains afterwards, 1 to the r is still 1. So it's congruent to 1 mod p. Okay, so u sub t factorial plus L is, I just plug it in, right? I have this formula, so I plug in for n. So it's qj of t factorial plus L, lambda j to t factorial plus L. And obviously, t factorial contains a factor of p, but p is congruent to 0 mod p. So that t factorial goes away. I just get qj of L. And here, I've just seen that the lambda to the t factorial, lambda j to the t factorial is just 1, and I'm just left with the lambda j to the L. But by definition, this thing here, by definition, is ul. So I've just shown that u sub t factorial plus L is congruent to ul mod p. Okay? Okay, so in particular, u sub st is congruent to u sub, is equal, that's the definition, it's equal to So if u sub st, which by definition is equal to u sub t factorial plus sf of t equals 0, then u sub sf of t is congruent to 0 mod p because it is congruent to u sub st mod p. But it's actually, that's a bona fide 0. So this guy must be congruent to 0 mod p. Now, this is true for all p that is prime, such that p to the d is less than t, and p does not divide delta. So it's going to be true for their product. So I'm going to take the big product, capital P. And this congruence still holds. And now what you can show that if t is sufficiently large, you just do an asymptotic analysis, but in fact, this is all effective. P is bigger than u sub sft. You just need the growth bounds and so on. So what do we have? What's the punchline? You have a number that's congruent to 0, okay, mod p. So p divides a number, and p is bigger than the number. What happens then? P is bigger than the number, yet p divides a number. What's the conclusion? The number has to be 0. So for t large enough, if u s t is 0, then u sub sft is 0. Okay, so this is very nice. You've got u sub t here, and if you have a 0 of this linear recurrent sequence, then you have an earlier 0. But you remember that f of t brings you back. You guys I should be doing it this way because yeah, okay. So if you have a 0 very far in the future, this cascades back into a sequence of zeros all the way back to at least, well, okay, we said for t large enough, but this is all effective. So you will cascade back zeros that are very far into the future back to where you are now. Okay, this is the idea. So what do? You build a sandbox where you can catch all these zeros. You can detect all these zeros, like a muon detector or something. And if you detect no zeros, then you know there are none. Okay, so this is the idea. And so you find n sufficiently large so that un has no zeros in the interval Sn, Sl, where L is the largest integer such that f of L equals n. So that's the construction. That's your sandbox. And then you know when, and by the way, you can always do this. There are finitely many zeros by the Skolem theorem. So eventually you will find such an interval that has no zeros. Otherwise, there would be infinitely many zeros. And this is all, of course, looking for a 0, you just compute. So you know when you found this, you know that for any t bigger than n, u sub st cannot be 0. Otherwise, it would cascade back and you would catch it. Okay, so you have an explicit, so given an LRS un, you do all this, and you have an explicit upper bound on where the largest 0 can be. So you have a decidability procedure. So you have a universal Skolem set. Okay, does that make sense? Okay, so if you didn't follow all of this, don't worry. It's in the paper. It's a very short paper. It was a 5-page when we submitted, and we padded it a little bit. It was 6 pages. It's a simple argument. But now recall that the set is that, and it's very sparse. Unfortunately, it has density 0. So density, what do I mean by density? So if you look at the first, if you take S intersection 1 to n, this is asymptotically log n over log n. So it's very far from n, right? If you wanted to have density 1, or let's say density 1/2, let's say, you would need n over 2 or something. No, this tends to, the density of this set tends to 0, okay? You understand what I mean by the density. So when we submitted this LIX, we were happy the paper got in. We were very happy the paper got a distinguished paper award, but we thought this is a curiosity because this is not really useful, right? It's surprising that it exists. But then what we realized is you can actually build thick universal Skolem sets that are very dense. Okay, this is what I want to explain next. But before I do this, I just need another tool. And this is a very deep result of Schlicke-Weyl and Schmidt on Diophantine equation, exponential Diophantine equations in multiple variables. So I've phrased it in a certain way. The Schlicke-Weyl and Schmidt result is more general than this. But here goes. So there's an explicit upper bound on the number of non-overlapping, I'm not going to explain what this is, but we just go with the flow, non-overlapping solutions of the equations qj of b times alpha j to the q times lambda j to the b equals 0. So this sum, okay? In integers qb. So you've got qj, alpha j, and lambda j. And here alpha j, lambda j, they're complex algebraic numbers. And the qj are polynomials with complex algebraic number coefficients. And you're looking for a pair qb integers such that when you plug in the B here, the Q there, and the B there, you get 0. And what Schlickova and Schmidt tell you is that there's an explicit upper bound on the number of such solutions. So non-overlapping solutions. If you allow overlapping solutions, you can't have many, but you can weed out these guys. Okay. So that's won't tell you what it's a simple definition. It's not like I'm hiding something, but I just don't want to say what it is. Yeah, Philippe. Effective. Yeah, explicit in the sense they wrote down like you can write down it's like k to this. It depends on the height and the degree of these guys, and it depends on, and it's all explicit in terms of you can write it down. Yeah, so definitely effective. Okay. So we'll come back to this. By the way, this is a deep generalization of the Skolem-Maralek theorem, because if all the alpha j's are 1, then you get qj of b times lambda j to the b, and it's telling you there are only finitely many solutions, so finitely many zeros. Okay, yeah. No, I didn't explain. I'm not going to explain. I can tell you afterwards. It's a simple condition. It gets technical. I'm just trying to give you some ideas. I obviously cannot give you all details. This is a lot more technical than the previous result. Okay. All right. Everybody, any other questions? Okay. So I'm now going to introduce a denser universal Skolem set. So here's the construction. It's a more elaborate construction. Just bear with me. So given a positive integer parameter x, so x is an integer, but think of it as a parameter, define two sets, a of x and b of x. They're intervals. You go from log 2 here is not log base 2, is log, iterated twice. So log x to square root of log x, and b of x is log x over square root of log x, and 2 log x over square root of log x. Okay, so you got these two intervals. These are small intervals, by the way, okay? Because square root of log x is a relatively small number compared to x, and here is the same thing. So these are small intervals. Not just small, but the upper bound of these intervals are small. Think of it this way. And now we say that a representation, given the number n in x to 2x, a representation of n is a triple p, q, b, such that n can be written as p times q plus b, where p is a prime, q is in a of x, b is in b of x. Okay, so I'll come back to this. Let R of n be the number of representations of n, number of distinct representations of n. And now you define S of x. We're coming to the definition of the set. So it's the set, so it's parameterized now on x. So the set of n in x comma 2x, such that R of n is bigger than log 4 times x. And finally, you put S to be the union of S of 2 to the k, where k is in n. So you take all these intervals, these dyadic intervals, you take the whole union, that's your set. That's your set S. It's infinite. It's not completely obvious, but it is actually infinite. And the theorem that we have proven, so this is under review for MFCS, is that S is a universal Skolem set of strictly positive lower density. Actually, the strictly positive lower density was actually proven last year on a similar construction, also published in MFCS. Moreover, assuming the Bateman-Horn conjecture in number theory, S has density exactly 1. And now, the number theorists believe this conjecture. So this is a universal Skolem set that has density 1, meaning it contains almost all integers. Okay, so there's a lot to digest on this slide. So let me just try to take you through it. First of all, I have a number n here, and I'm asking that this number n as a representation of the form pq plus b. Now we know the prime number theorem tells you n can be written as products of primes. This is not what I'm doing. I just have one prime p times q, which can be anything, and then I can adjust my offset with a b. Now q and b are small. Okay, q and b are small, but p can be chosen arbitrarily. So depending on how the primes are distributed, I can hit a lot of n's, right? Because I just need to have a p that's sort of the right, well, my target n is here. I find a p and a small q, relatively small q, that gets me close to p, and then the b allows me to reach p, okay? Now, what I want, though, is not just that n has one representation like this. I want that as n gets larger and larger, I want that n has increasingly many representations. A number that grows, a function that grows very, very slowly, log of x goes super slowly, but it goes to infinity, but super, super slowly. The reason I want it to go slowly is I don't want to make the bar too high. I want to allow a lot of n's in my set, as many as I can. So I ask for a number of representations to be low. but I do need that to go to infinity. Okay, that's the idea of the construction. Okay, maybe it's a lot to take in, but let's just go with this. So the first thing is this set that we've constructed. It's well defined. It's constructed. This has strictly positive lower density. This is a very technical result. It's a combinatorial argument that involves two key ingredients. I'm not going to give you the proof, but I'll tell you what the two key ingredients are. One is sieve techniques. So these are the prime number sieves, and especially the Selberg upper bound sieve for linear forms. And the second is using the so-called moment method together with the Cauchy-Schwarz argument. So you put these things together. So I mean, basically, just to give you, I'm not trying to be mysterious. How are you trying to count the set? So you want to know, how many n's in a given box of x to 2x do I have, right? So I want to know how many different n's can I reach, given that I can play with a b, play with a q, and I can choose any p. So you need to know something about the distribution of the prime speed. They're unrestricted. And then the b and the q, they live in a small box, and you can take any one of them. So you count all these things, and you basically get the density. And in fact, the calculations show that we can obtain unconditional density at least a half, probably more. But perhaps the most interesting thing is that if you assume the Bateman-Horn conjecture, and I'll say something about this in a sec, S is actually density 1. So asymptotically, you're containing basically almost all the integers. Unfortunately, there's a set of density 0 that you're missing that is infinite. Well, we cannot prove this, but again, if you assume standard heuristics about distribution of prime numbers, you find that yes, there is a very sparse set that you're missing. So you don't get all of the integers. What is the Bateman-Horn conjecture? I've put it here. Let's just go quickly through it because it looks very intimidating like this, but actually it's not. So you have a bunch of polynomials, k polynomials, okay, that are distinct irreducible, okay, with positive leading coefficients. And now you have q of these polynomials and x. X is an upper bound. So you're trying to count the number of n less than x such that these guys are simultaneously primes at n. Okay, so you let q be the counting function of this set. And the Bateman-Horn conjecture, okay, you have a technical condition here. And the Bateman-Horn conjecture says that this function q asymptotically is equal to this function c of these polynomials divided by this product of the degrees of the fi, that's easy, times this integral, which looks very much like a power of Li of x, right? If you're number theory, the prime number theorem, this function, of course, without the k, you get the standard the standard Li of x logarithmic integral of x, and now it's a k because you have k of these forms. And this function c is given by this product. Okay, it looks completely crazy if you don't, First of all, I should say we're only using the Bateman conjecture with two of these guys, and they're not arbitrary polynomials; they're linear forms. So that simplifies things. So this is Bateman, and this is Horn, and this conjecture. It's a central unifying and far-reaching statement about the distribution of prime numbers. It's similar in that way to the Riemann hypothesis. It implies many known results, such as the prime number theorem, the Green-Tao theorem, many famous conjectures, the twin prime conjectures, Landau's conjecture, and has been described as ranking among the Riemann hypothesis and the ABC conjecture as one of the most important and pivotal unproven conjectures in number theory. Okay, so it's essential for number theory. You probably never heard of it, but for number theorists, it's a very important conjecture. And if you assume this conjecture, our set is density 1. Okay, so let's continue. So I want to show here. This is the last technical thing that I'll be showing you, but I think it's important to show this, or at least it's perhaps interesting. Why is S a universal Skolem set? Why on earth, my crazy thing with the represent, why is that a universal Skolem set? What does this have to do with linear recurrent sequence? Let me try to explain this to you. So there are many parts. This is a very technical proof, and I can only give you one of the ingredients. It's one of the key ingredients, but there are many other ingredients. But let me give you this one ingredient. So you write un again as before as this exponential polynomial, and suppose that un is 0. And suppose that n belongs to your set. So n is representation, in fact, many representations of the form pq plus b. Okay? So I'm going to assume this. I have found a 0 in my set, perhaps very far, very large n. Okay. And what happens then? So 0 is equal to qj of n. So qj, I just replace it here. Lambda j to the pq plus b. Okay. So this lambda j to the pq plus b is lambda j to the p to the q times lambda j to the b. And now I want to take this equation modulo p. So if you remember from Fermat's little theorem, lambda j to the p should be congruent to lambda, or lambda j. But for algebraic numbers, you actually have to apply a Frobenius automorphism. So this lambda j to the p becomes sigma j of lambda, and now it's raised to the q. This qj of p, of course, works fine. And this lambda j to the b is just here. And p here is a prime ideal lying above p. And sigma, like I said, is a Frobenius automorphism. If you don't know what these things are, just ignore it. Just go with the flow. The point is that this is not anymore. This is a complex number. In general, this is not a real number, okay? Because we've now this, but there's a prime ideal that will divide this number. That's the whole point. And that prime ideal lies above p. The consequence is that p will divide the norm of this number. So this is the field norm, an algebraic number. So it's the product of itself with all its Galois conjugates. And that's always an integer. And this capital P divides the norm. Now, here's the punchline. Q and B are small. Remember, Q and B were chosen to be small. But if n is very large, Q and B are small. So you've got Qj of something small times sigma of lambda j to something small times lambda j to the b. This is still relatively small. So this norm is small. Okay. So if n is large enough, P will also be large, because what is P? N is P times Q plus B, but Q and B are small. So if n is very large, P has to be very large. In particular, P will be bigger than the norm of P will be bigger than this norm, than this integer. So we have the same trick as before. P divides a number, but it's bigger than it. That means the norm must be equal to 0. If the norm of something is 0, the something must be 0. It's an honest to God norm. So this thing is 0. Okay. What's the punchline? The punchline is this. If n is large enough and un is 0, and n is the representation of this form, then this sum is equal to 0. That's what we showed on a previous slide. Okay? But now recall this theorem that I quoted. There's an explicit upper bound on the number of non-overlapping solutions of the equation. And this equation looks suspiciously like this. I mean, the sigma lambda j is alpha j, but other than that, it's the same thing. So you have only finitely many QB solution to this equation being equal to 0. Okay? But each representation PQB of n, remember, un is 0, but n has many representation. It was a function, the number of representations tended to infinity. So each of these representation gives rise to a solution QB of this companion equation here. But there's an upper bound on the number of solutions of this thing. So at some point, you have too many solutions, and therefore un equals 0 is just not possible anymore. Okay? So as the number of representations of n tends to infinity, but the number of solutions to the companion equation is explicitly bounded, this yields an effective upper bound such that un equals 0. Okay, does that make sense? Yeah?
When you talk about the bound, where you said that bound depends on the equation, but the equation what is the growth of the bound?
So the equation is fixed because Qj, so Qj is fixed, right? Qj depends only on the linear recurrent sequence. Oh, the bound depends on okay, the bound here. So you look at this theorem, the bound. So the equation Qj is part of the data, alpha j is part of the data, and lambda j is part of the data. And the bound depends on the height and the degree of these numbers as algebraic numbers and as polynomials and so on. And it's a fixed bound that only depends on the degree and the height of these things. So now you say you plug in B, you plug in Q, and you're saying there are only finitely many BQ that you can plug in. Yeah, it's completely, yeah, that's a good point. So it's independent. Oops. And so yeah, so you get this bound, and therefore as the number of representations of n goes to infinity, you get too many solutions to this companion equation. So at some point, you get an explicit upper bound such that beyond this upper bound, un cannot be 0. Okay, so this is my last slide. where are we going with this? So this is the idea of the concept of universal Skolem set. It's a radically new line of attack on the Skolem problem. It's not sort of looking at the characteristic roots and looking at these things. It's a sort of, I think, completely different way to look at the problem. We have not solved it. We've exhibited a set that has positive density, probably density 1, if you believe this conjecture. And so there are several directions, but perhaps 2 critical directions here that I want to mention. Is there another construction that would give us a universal Skolem set containing some infinite arithmetic progression? So by the way, if you have density 1, in fact, if you have strictly positive density, Zermedi's theorem, for which you won the Abel Prize, tells you that you have arbitrarily long arithmetic progressions in your set. But you need an infinite arithmetic progression to solve the Skolem problem. So we're not there yet. But I should say something else. If you have a universal Skolem set, if you shift it, it's again a universal Skolem set. If you have 2 of them and you take their union, it's again a universal Skolem set. So if you have a universal Skolem set, or if you've got 2 of them, you can take their union, you can shift them, take their union, you can even do some infinite reconstruction. You're still a universal Skolem set. Can we play with these things and then say, we've got all the odd numbers in there or something, right? Could we do this? If we could, we'd have solved the Skolem problem. Another question is, can you apply these ideas to other problems, such as the positivity problem, the ultimate positivity problem? So this is, for the Skolem problem. There are obstacles to doing this, but who knows, right? So thank you. I'll stop here.
Density is important. And you just
so okay, so density, if you're trying to solve the Skolem problem, you're trying to show that n is a universal Skolem set, right? The most simple. So density is a means of quantifying how far is my set from containing all integers. If you have a very sparse set of density 0, like the prime numbers, they're very sparse, they have density 0. You're not containing all integers, you're missing most of them. Most numbers are composite. But if you have, let's say, the composite numbers, that's a very dense set. Most numbers are composite. So now you're getting closer to getting all of n. So density is some kind of proxy for how close or how far are we from the natural numbers. It's not, you might say, okay, why this proxy, why another? So number theorists always look at density of, so Terence Tao, for instance, had a spectacular result, I think last year or 2 years ago, where he looked at the Collatz problem, the 3x plus 1 problem. And he showed that the set of numbers that do not go to 1 of density 0, something like this. I mean, so he showed basically the vast majority of numbers actually obey the Collatz conjecture. If you could show all of them do, then you've solved it. So it's a proxy that's often used to quantify progress towards a goal.
I have a very basic question that shows my ignorance. At the beginning, at some point, you said that there is a power of a lambda which is congruent to 0 mod p.
To 1 mod p. To 1 mod p.
To 1 mod p. And I wonder, what does it mean when you have something which is not an integer?
So lambda is an algebraic integer.
Yeah.
So you have a notion in algebraic number theory, you have a notion of any algebraic integer can be written as a product of prime ideals with unique factorization. So it's an extension of the factorization of integers into primes. Algebraic integers get factored into prime ideals. And if you have a prime ideal, it then makes sense to say a prime ideal divides a number. And so now it makes sense to say a prime something is congruent to something else, because that means a prime ideal divides the difference between the two. So it's a concept from algebraic number theory that sort of reintroduces unique factorization into algebraic numbers. You know that algebraic numbers, they do not obey unique factorization if you do it naively. So this whole concept of prime ideals was introduced to recover unique factorization. So it's It's from algebraic number theory. Yeah. I think it's for the Zoom people.
There are no Zoom people. So I had two questions. One is related to maybe Paul's question. So is it possible? So if I have an infinite arithmetic progression in a Skolem set, but it's not dense,
Oh, so if you have an infinite arithmetic progression,
it must be fully dense.
if the period is say R, then you're at least density 1 over R.
But is that so that's good enough, right? So you just
Yeah,
want
yeah, that's
density
good
to
enough.
be okay.
Yeah, you don't need density 1.
Right. That's
I mean, of course, once you have 1 over R, you
You're
can
done.
shift it,
Right.
union, shift it, you do this R time, you got all of N.
good. Right.
So yeah.
And second question is, you started in the beginning a lot about simple sets.
Yes.
There's no simplicity here.
And no, so well, the MFCS paper did this construction only for simple LRS.
Okay.
And it was a lot simpler. So what this new paper does is it circumvents a lot of the difficulties associated with non-simple LRS. So these details I've completely elided. This gets very technical, but yeah. So yeah. So, that's the so simple sequences are usually easier to handle, of course. Yeah.
But I mean, is there something special about arithmetic progressions? I mean, it would be good to have. I mean, with arithmetic progressions, you would end up solving the problem, right?
Yes.
I mean,
And you're saying what's magical about arithmetic progressions?
yeah,
They're a copy of the integers.
yeah. No. What I'm saying is that is there something between, what you already have is. I mean, the results that you showed, you already have some universal Skolem sets.
Well, if you have sorry, no, I guess I don't understand the question. Is that...
No, I mean, I'm saying that you already showed that there are some universal Skolem sets.
Yes, absolutely.
And clearly they don't contain an infinite arithmetic progression.
Well, we actually don't know for a fact that they don't. We suspect they don't. If they did, you would have now solved the Skolem problem outright.
Right.
Yeah.
So what I'm saying is there something in between?
In between. Okay, that's a good question. You will need an infinite arithmetic progression in your set. If your universal Skolem set allows you to solve the Skolem problem, then you will need to have an infinite arithmetic progression. You're not going to be able to do without. Because ultimately, it means that N is, if you solve the Skolem problem, it means by definition, N is a universal Skolem set. And that contains infinite arithmetic progression. So you cannot somehow circumvent that.
Long live India and France friendship.